Welcome to the lecture series on object-oriented analysis and design. We have taken a very clear view on why object-oriented as a paradigm has been showing very good results in the field of software engineering for a wide range of applications that has a complexity that grows at a very fast pace. So, we have been saying that object oriented paradigm and related technologies are very essential for developing complex software as it evolves. In the beginning it may be only this much, today we have only 10 vending machines, tomorrow it may be 1000, day after tomorrow it may be 10,000. So, we are talking about a very nice way of building scalability, managing them without reinventing the wheel. By saying so, we are not indicating that object oriented has just happened in vacuum. It is built over a span of clear 4 to 4.5 decades before it has gone into the main focus, saying that it is almost the only solution now to address complexity. We have had very good principles, we have had very good concepts, nice ideas like phase, nice ideas like life cycle, which have been well documented by 1985. The software engineering field itself is very nascent, it got a definition for itself in 68. 69, that is those 2 years NATO conferences have given us a very concrete definition for software engineering. The very nature of software engineering has always been like that. It has been true that there was a roaring success, the space program in the US happened with very good software, Unix was a roaring success, but still we found that many other efforts, an alarmingly large number of efforts, were not really so successful to tell that yes, this is what has happened. So, we said let there be a definition. It is not that a few groups are able to come together and make it happen. If the field gets defined, that high potential of software will automatically improve the quality of life, will definitely make better things happen, and they are happening even now. So, in a short span 1970 to 2020, that is 50 years, a remarkable progress has been made in the field of software engineering, and it is more promising now because it has already permeated across every activity that you and I are doing today. If we are not having a software in the loop, we should be shocked. Whatever we do, whether it is a small activity, big activity, complex activity, there exists at least one line of software that is making us do whatever we are doing, we are accomplishing. So, quality of life, all these aspects have been discussed. We do know that the very nature of software engineering is like that. The success rate is around 36%, which is very good because it is only 50-year-old profession, very nascent and a very young engineering profession, still trying to come up with a concrete way of telling what is science and what is engineering in what we are doing, but still we say that it is a remarkable progress. 36% success rate is a remarkable progress in an engineering discipline that is just barely 50 years old. And for the next 20 years after 1970, it was more like putting these definitions to test. It did not happen overnight. Putting these definitions to test, 68, 69, let us say 70, we got all necessary definitions in place. Next 20 years, definitions in place and definitions in what is called putting to the test of time. Everything was nicely tested, the principles got documented by 1985. So, we keep telling the same thing, that even though all of us have the same uncertainties, all of us have the same concerns about software, we have learnt how to do things about phase. What is it to be phased, how to earmark a phase, every phase has a separate team, ideally every phase has a separate notation, the demarcation of the phases is very clear, on paper it is very nice, but the true strength and the presumption of the entire success is that the requirements are cast in stone, they are all frozen. In reality, there is nothing called frozen requirements. So, 20 years after 1970, we reconciled to the fact that these are all great principles. We will have to wait until the testing phase happens to test anything, otherwise we are only trying to find out whether are we on the track, are we progressing. Only after the testing phase begins, we talk about testing, defects, bugs, all getting properly identified, reported and everything. Otherwise we are talking as teams. We do not know who gets the next idea, who gets the next brilliant idea to put up a procedure. So, we have been talking, we understand, we develop programs primarily through debugging process, all that we have been talking about in these past several lectures. However, the core question remains that the requirements are seldom frozen, nothing is cast in stone. Every time we are talking about volatile requirements as the number one villain in our exercise, and we are talking about 36% of success at a very high end of operations. Typically, we are ranking around 10 to 16% of success rate in normal organizations. Typical organizations, if they get into double figures of success rate, they are doing very well. 36% is a very high end. We talk about lot of organized activity, plenty of technical depth, people, machines, tools, procedures have a very great synergy and it has evolved over a span of time. So, that is when we talk about possibility of touching that maximum peak of 36%. What I am talking about is a range, the maximum. Good number of organizations today are showing 36% world over. So, that is a good confidence with which we move ahead. Next 20 decades, next 20 years, we are talking about many more progresses that are already being envisaged will happen. So, for all these things, we are talking about complex, evolving systems. We need to talk about that complexity which we celebrate. We need to acknowledge that instead of talking about volatile requirements, change requests, we simply acknowledge that systems will evolve. It is easy to talk about systemic evolution rather than get bogged down with requirements, requirement analysis, change request, change impact analysis. Not that that was wrong, but then we have now brought in the systemic approach to tell that they are evolving systems. Today it is like that, tomorrow it may be something. Today in our organization, only 3 pieces of software are there. Next 10 days later, we may get 30 more pieces. Are they working together? Should we want to work them together? We keep saying the same old story all along, that since we do not have a grip on software engineering to the extent which we wish to have, like in other engineering disciplines, we have a deliberate tendency to first build broken systems. We want to build them because if a fault occurs, it is local, that is the assurance which we have. Even without testing, I can tell that if a fault occurs, it will be localized. It is not likely to spread its tentacles. Why is it so? This is what we have been talking about. Bettenmeyer, in the last few lectures I have used this slide, I am reusing this slide, it is worth reusing this slide. Bettenmeyer is a French academic, author and consultant in the field of computer languages. He created the Eiffel programming language and the idea of design by contract. We all want our software systems to be fast, reliable, easy to use, readable, modular, structured and so on. In object oriented, we keep adding that one important aspect of object oriented, namely encapsulation. It is there, it is a chip, it will be there. Even if you want to find out, you can't find out what is happening inside that. So, we can stretch the idea of broken systems up to that point. Why? Because you are assured of a localized fault. If something goes wrong, it is definitely only in this particular broken component of a bigger system. So, we have built by definition an enterprise that is appearing as islands of software, which they may not want to talk with one another. Now, the challenge is how do we integrate? Object oriented gives us a very nice idea of integrating outside of the service oriented architectures like cloud, another service oriented architecture like web services. We all want our software systems to be fast. When we talk about software systems, we normally talk about the enterprise wide context. Software systems to be fast, reliable, easy to use, readable, modular, structured, and so on. But these adjectives describe two different sort of qualities. On one side, we are considering such qualities as speed or ease of use, whose presence or absence in a software product may be detected by its users. Till today, there is no escape. Nobody escaped this law. You see in the world what you want to see. Nobody has escaped this law. So, what we are looking at is, we are first looking at speed, ease of use, whose presence or absence in a software product may be detected by its users, not technical experts. People who are using it will simply tell that, yeah, it's fast enough, the response time is good. So, these properties may be called external quality factors, where the developers are not at all concerned about observing such things, but they have to play the tune. It is not the primary goal. It happened many things in software development were an afterthought. User interface was certainly an afterthought. Testing we want to avoid. As far as possible, you avoid testing. Already the quality assurance people are writing nasty reports. On top of it, if you make a testing phase, we have even more serious concerns. So, these properties may be called external quality factors. Other qualities applicable to a software product, such as modular or readable, are internal factors perceptible only to computer professionals. So, what is the basis of talking about quality factors? Every quality factor is important. There is nothing like not important quality factor. The number of quality factors, there is a huge debate until the quality framework stabilized in year 2000. Now we talk about a quality framework, a process based software engineering, which tells that there is a quality framework, capability maturity model, or you talk about ISO 9000, 2000. So, that is how it is. Other qualities applicable to a software product, such as modular or readable or internal factors, perceptible only to computer professionals. So, out of all these quality factors, definitely there are certain internal factors, there are certain external factors. External factors are by the users who normally want to use that software. In the end, only external factors matter, that is, quality is best reflected when people who do not know anything about the software talk about it, not the developers. That is a simple implication of this wonderful passage. In the end, only external factors matter. If I use a web browser or live near a computer controlled nuclear plant, little do I care whether the source program is readable or modular, if graphics take ages to load, or if a wrong input blows up the plant. But the key to achieving these external factors is in the internal ones. For the users to enjoy the visible qualities, the designers and implementers must have applied internal techniques that will ensure hidden qualities. By the same token, we keep telling that please do not bother too much about what is hidden in the encapsulated object. That is not your first concern. First, talk about the external quality factors. We do agree that there cannot exist great external factors with some kind of an arbitrary internal quality factors. They cannot exist. It cannot simply happen. This is a framework, this is a capability maturity model which integrates all these well, but for a quick understanding, it is always possible to judge from the external factors what might have been the internal quality factors. So, we have come to a conclusion that to understand the total quality, there is no need to make everything transparent, or everything is going to be what is called white box. There can be components, there can be black boxes, and that is giving the real speed in software construction. Object oriented software construction will require that kind of an understanding that there will be black boxes. We should know how to work with black boxes. The same is true with cloud computing. Are we worried about who is the cloud provider, service provider so much other than a service level argument. Same is the case with design by contract in object oriented. A service level agreement is there, it is good enough, you have signed. So many of us are using the tools. If you are quite contented, satisfied, then we should be able to go ahead with that. So, we have gotten accustomed to using black boxes, at least the black boxes kind of a variety of software in our day to day work without getting too much of a doubt at every step. There are doubting Thompsons, we welcome doubting Thompsons, that is how we progress further, but then we know that it is quite possible to look at those external factors to make a judgment on what is the internal factor, internal status of internal quality factors. Object oriented software construction. So, the point is, when we are talking about enterprise application integration, in theory we agree that the design is good when there is more monolithic or sort of broken systems, clearly identified separate components. However, we know how to integrate them. That is the essence of integration in complex systems, which we should understand. It is true, the idea is correct. We need to understand that they are broken systems, they are black boxes, we need to integrate them. CORBA as an interface definition language has established well. We talked about common object request broker architecture. It is an interface centric programming. This is what we talk about. It defines those interfaces that reflect the external quality factors clearly, and if it is happening like this, please do not worry about the internal quality factors. Even if it is just a black box, you can simply connect and go ahead. We did it very well in engineering disciplines. For some years when I was doing my engineering, civil engineers were talking about the next best innovation. That time it was something which was great, called prefabricated concrete. So, they make walls, they make roof, they make everything, and then they will simply tie up the ends and it will become a house, it will become a structure of your choice. I don't, it is a vague recollection, but that is how it is. Much later, when I came over to Chennai, there was this idea of low cost housing, where they were talking about such provisions made out of a simple material, and then you can ship that material anywhere. Very quickly you can construct a place with a roof and 4 walls to get on with the job. We need not know too much about what is that material, it is just that we fit it. The same story which we talked about in the case of a Meccano, there are about 30 to 40 components from which you can generate about 40 to 50 different artifacts. You can try it out, how fast can you do is the only question. So, it is possible, it is definitely feasible. It appeals to your natural common sense way of working, that we can work with black boxes, we can work with components, provided the interface definition language is reflecting the internal quality factors, which will be experienced as external quality factors by any user. Language specific compilers will translate ideal specifications into language specific source codes that is used to implement those interfaces. Ideal is a bit higher than what is called a typical programming language. It is more abstract. You can go higher and higher and then keep telling that once it is in ideal, you have to simply select a programming language, the code will be automatically generated. The grammars are specified. All that we are trying to implore is that ideal is a nice way of fitting a given component or an object in its context. That is how it interfaces. Interface centric programming, one more centric programming. Suppose the user centered, interface centered programming. Suppose the server is written in language L1 and the client is written in L2. Define an interface I of server object by CORBA ideal. Compile I to I return L1, the server object. The point is, we need to have an interface in between two pieces of software, one written in L1, one written in L2, two languages. How do we do that? What is the way in which these two languages talk about? As an MTech student, there used to be, we used to go to the library, that library was talking a very nice book called Mixed Language Programming, which was always in the reference section, because no student was supposed to talk about mixed language programming. If you have chosen C, you think C, you talk C, you work with C, your program is in C, your C compiler works, everything is only C. There is no way in which you can think of anything other than a language called C, ANSI C. That is how we have been. So, there used to be a curiosity saying that there is this book somewhere called Mixed Language Programming. What was the impetus? Somehow we want to get connected to the rich libraries which are already written in Fortran language. Fortran 77 libraries were already there. If we have to have mathematics, then you need to link up to the Fortran 77 libraries. How do we mix these two languages? Here we are talking about a client and a server, there we are talking about a program and a library. Wherever there is a need for connecting pieces of software written definitely in different pieces of language, we can talk about this IDL, very first pragmatic use of IDL, because now we can't dispute they are different languages, different language segments. We are not talking about mixed language programming, it's not at all like that. We are talking about building a common layer, acceptable common layer called common object request broker architecture interface definition language, which is language neutral. Interface centric programming, the client object creates a reference of the server object that has I as an interface. We keep talking about the same. The outcome of this IDL is there will be, let us say, the client fellow talking about one object in language I, the server fellow is also talking about one object with same language I and I talk to each other, the client talks to I, the server talks to I. And now the problem is solved. In the world of remote procedure calls in the distributed computing, we call them client stub, server stub. There is a commonality which we have established in the client stub and server stub. All this is now nicely abstracted out as interface definition language. The client will create one object in language I, that is the interface language. The server will create another object in I and I talk to each other. The client and server are therefore connected. It is a nice way of telling that without talking about mixing up languages, without talking about cutting open the code to make some such stubs or whatever, even as black boxes, Corba will facilitate how to put them together. C++ IDL syntax is much like C++. We always had that tendency to tell that IDL is nothing but C++ with some nice more frills. As students, all of us had that opinion, but then as we progressed, we know that it's better to avoid such similes. With C++, it looks like it, it's based on it, but IDL is different, it's IDL. Corba is an infrastructure for building distributed applications. Servers advertise named objects with known interfaces. Client uses these names to create references to server objects in order to invoke their methods. So, all this is fine, but why do you believe that it is working? Please wait until the testing phase. There should be a testing phase. Only then we can comment on whether it is a correct solution, working solution. Until then, we are talking about giving some random test cases, finding out if the program is working. It's a programming world. Until unit testing starts, even if it is a unit, single unit of code, we are not talking about anything on working, correctness or whatever it is. So, defect severity, all that should be in the programming. We take care of all that. So, what is special about object oriented testing? It should be systemic, because we talk about top down analysis and then something coming from bottom up simultaneously. By definition, object oriented testing ought to be systemic. Integration testing flows most of the time. Unit testing, integration testing have a common point. We are not likely to have the testing phase split into clearly unit testing, clearly integration testing. Most of the times unit testings pass, but then when the units are put together, nothing works. So, we have attempted to solve those concerns, the top down, bottom up, unit and integration testing. In the traditional mold, we had these difficulties. Everything is correct about the unit, put together the units are simply not happening. It's like that. In practice, that is what happens. Maybe it's just at the very lower preliminary, some format difference, maybe it is something else. What is the reason why it is happening? These used to be big question marks. Object oriented has said that system testing, integration testing, unit testing all fall in line together in some jigsaw puzzle pattern based on inheritance, polymorphism and encapsulation. The three basic ideas, and these are reflected, all this is reflected as state and behavior of an object. The object has an identity. If this much is understood, now we will see why object oriented testing is faster, more economical on a longer run. We think that the components are already there, you have to see all pre-tested, prefabricated, you have to just connect them together with ideal, it should work, any orb should work. Traditional development testing, requirement specification, this is what I have been talking about. We have covered by the terms like system testing, integration testing, unit testing. We have brought in all those earlier phases, requirements, preliminary design, detailed design into the natural flow of testing. It happens like that. There is a systemic testing, system testing, integration testing, unit testing. We do not talk about requirements, elicitation, gathering, requirements verification, design rule checking, all that are set aside. Once you start object oriented testing, there is something very inherent in object oriented testing that makes you look at all these three together, system testing, integration testing, unit testing as a part and parcel of object oriented testing. Traditional test, now please understand that testing is another serious challenge, much like its advanced cousin verification and validation which needs more formalism. Testing is also a very serious concern. We need to understand what we are testing for. What is the reason why a test case is given? It is fine to talk about random test cases generation while we are in the development phase, but once it is done, once it goes into the testing, every test case is reflected as a cost factor. That is how we curb those tendencies. If it is a test case, it has a cost. Every test case costs, every testing type costs. System, integration, unit. It is good in business to shift many things to time and money. That is a nice indicator. Those two are time tested business specifications which are undeniable. It talks about a business sense in a very nice manner. So, shift everything to cost and time, and that is exactly what we did in the beginning, until we realized that in the field of software engineering, while the business requirements are there, the business domain, the business acumen, the business way of working, everything is there, all reflected as, let us say, cost, time, work breakdown structure, tasking and everything. Quality reigns supreme because of the aforesaid reasons. Because of all the things that we are talking about in this lecture session, quality reigns supreme. Over development and testing, development based on behavior. Object has a state, object has a behavior. Composition, typically rapid prototyping, incremental approach. Three traditional testing levels are not as clearly defined. So, what we need to understand is, we have been talking about these levels of testing, the traditional testing, system, integration and unit. There is so much of gray area in all these things. We did not have a systems approach in the beginning, we only had phase, we had phase wise clear demarcation of everything, how they combine as life cycle, nothing wrong about it, those are still the foundational principles. You cannot keep doing everything each time 24/7. We should have some way of working. There are certain standard life cycle models. If you are using life cycle models, you are not likely to err so much. That is what we keep telling. The context in which this is happening remains a very big challenge in itself. As I said, lot of companies which are still known in the field of software roughly rank between 10 to 15% success rate. 36% success rate is really top rung. We are seeing a good density emerging now, which is good. The kind of software that's being developed. So, 3 traditional testing levels are not as clearly defined as in object oriented. So, object oriented development and testing are actually going hand in hand. There is no real serious testing phase for a component, because by the time the component gets its specification, it is nicely tested like a prefabricated concrete. It is that the brick is there, we accept it, no questions asked. It is just that you have to look at certain parameters to see how it fits into the overall software construction. So, development based on behavior, composition, typically rapid prototyping, incremental approach, gradually we build. The 3 traditional testing levels are not as clearly defined. So, with this we say that object oriented testing is distinctive. It has high advantages of bringing all those top level phases which are conceptual into a concrete software construction method, quietly building both internal and external quality factors together. Thank you. We will meet in the next lecture.